Everyone, welcome to Silicon Valley Quantum Computing Group. Today's talk is on atomic clocks. We have Dr. Lawal with us. He's going to talk to us about, of course, atomic clocks and quantum sensors in general. About me, I am a director of innovation at a company called Kaiser Permanente. And my work is focused on digital twins, machine learning, and simulation. Of course, I am the author of the book, couple of books, Intelligent Governance for both the quantum as well as the classical computing era. And that's where my intersection to quantum computing is. I'm very interested in quantum sensors. I have a physics graduate school background. So that's something that excites me. I have a host with me, co-host, Divya. She's a student volunteer. She helps me getting organized. So Divya, thank you. If there is any other announcements you want to make, let us know. Otherwise, we'll move on and without wasting much time, introduce Wale. Anything from you, Divya?
No, thank you for the introduction.
Okay, perfect. Thank you. Thank you. I'd like to introduce our speaker, Dr. Wale Lawal. He's a second-year student at Harvard Business School. He is co-founder of Mesa Quantum. It's an early-stage quantum sensing company that also makes quantum atomic clocks. I had the opportunity to meet the other co-founder, Srishti, as well, who was originally going to be in this talk, but she had an urgent visit to South Africa, so she requested Wale to help us with the presentation. So thank you, Wale, for presenting us these things. Prior to Harvard Business School, Wale served in the military for 8 years as Air Force engineering officer. And then prior to that, in the Air Force Academy, he earned his bachelor's, and then he went to school at Rice University for the master's, for the PhD program in material science and nanoengineering. Dr. Lawal has both the business acumen as well as the technical acumen to explain us quantum sensors and in this topic, quantum atomic clocks in some detail. So we are looking forward to this discussion. I'm going to just share 2 more slides and then pass the ball to Dr. Wale. So agenda. Today is, of course, the sensors. We'll have a fireside chat just to prime the pump and have some discussion going, and then we'll open up for Q&A. I'm sure there's a lot of question about quantum atomic clocks and security and the intersections of those things. Finally, I mean, this is a session overview. Of course, I sent it in an email to all of you, so you will see a variety of things being covered here, and Dr. Lawal will talk to us in detail. So without taking much time, Wale, I'm going to pass on the ball to you. I'm going to stop sharing so you can, and we'll take it from there.
All right. Thank you. Let me go ahead and share my screen here. Good morning or good afternoon or good evening, depending on the time you are in. Hopefully, you're having a good Saturday so far. Thanks for taking the time to listen to my presentation, and look forward to engaging in any conversation you all might have. I'm here on behalf of Mesa Quantum, which, again, we're an early stage company spinning out of a university labs, the Boulder, as well as NIST Quantum Institute, focused on how do we bring the next quantum revolution using advanced quantum sensing technology. And so just again, like at a high level here, again, like quantum technology, the race is on and it's begun. And a lot of research and investment has started to gone into quantum technology in 2021 and 2022. Both years individually saw about $2 billion worth of deal capital in this space across the 3 areas of quantum computing, quantum sensing, and quantum communication. Many people are familiar with quantum computing in the sense that that has been getting a lot of attention in the headlines and the news as people look to gain quantum supremacy and leverage that for new business value. And again, just to create like a quick distinction between the three, quantum computing is essentially leveraging these kind of quantum mechanics, quantum principles to offer accelerated computational abilities, thinking through how do we, model, create advanced molecular models for material discovery, or we think about optimization problems, whether it's in traffic flow or urban development, and leveraging this to accelerate those type of simulations. Quantum computing reigns supreme in there. Quantum sensing and quantum communication don't get as much attention, but actually, as you'll find out here, they're much earlier in the stage of like commercialization than quantum computing is. And these, leverage the same quantum principles and engagement in the kind of the quantum ecosystem, but for different applications. Again, quantum sensing is really in this sensor space where you are trying to gain high precision measurements, leveraging physical quantities. And I'll talk about what that means here in a second. And then quantum communication, again, that's just a kind of an offshoot where we think about, cybersecurity and how do we leverage quantum states actually as a vehicle to encode information and then decode it at the relevant point in time. And so again, as the Topash kind of mentioned, this will primarily focus on quantum sensing. We just wanted to kind of overall highlight the quantum technology space. I will say for quantum sensing, one of the things that excites me about it is how much the US government and even the broader international government has really gained a lot of interest in this area, this broader area of quantum information science, being quantum sensors and quantum communication technology. This year in particular, the National Quantum Institute even pushed out like a report just highlighting that this has been a pivotal year when it came to actually trying to work with government to institute policies that really help accelerate quantum sensors and the commercialization of it. You can see a few highlights on the right, just between a presidential directive being signed for quantum information science last year to really focus on, getting funding, getting things in the right place, standing up whatever institutes are necessary to see this adopted, requiring reports on quantum sensor development. And then, as you can see in some of the other bullet points, really creating an actual national strategy around quantum sensors so we can bring them to the market at a much larger scale, increasing R&D funds, almost 3x in the last 4 years between NIST, DARPA, DOE, across many of the agencies, and then even figuring out how do we start to increase workforce such that we have deployable workforce in engineering and manufacturing and the like as it relates to quantum technology. So the government's very interested in this space, and want to next just briefly talk about why and start to get into quantum sensing as a whole, and then dive in deeper into one particular topic of interest. But again, quantum sensors, like I said, we can see them as the holy grail for sensing applications. They are relying on fundamental building blocks that create ultra-sensitive measurements and extremely precise information depending on the sensing need. And once these kind of quantum sensors have been optimized, maybe through size reduction and other avenues, they're going to be able to capture information at such a level of accuracy and precision that is not even available on the market. And so they again, once they're commercialized at an exciting scale, you will start to see them, not only create new applications, but to completely just replace existing markets because of their performance. There's a suite of quantum sensors that are entering the market or have demonstrated some early success. I kind of bucketed it into like two different maybe generations of quantum sensors. The first essentially including devices such as like the quantum clocks, through microwave atomic clocks that we'll talk about a little bit more. Essentially what we use in GPS is a quantum clock that is fundamentally controls many technologies across multiple industries. And so that's something that, was integrated over the last several decades through GPS satellites. And then even like magnetometers, we think about brain image scanning technologies. They rely on quantum sensing of magnetic fields through brain imaging that has seen some success. And then now this kind of quantum 2.0 revolution that's coming to light as well is really focused on, how do we now essentially take the suite of really all of these 5 quantum sensing technologies and then start to disrupt the existing markets, like the MEMS, micro electromechanical systems that have become so popular over the last decade or so. They provide a certain level of performance when it comes to sensing, but these quantum sensors will eventually disrupt those markets, both in when we think about inertial movements through gyroscopes and understanding like a position, accelerometers, understanding how do we maybe leverage these quantum sensors for like autonomous navigation, autonomous vehicles through accelerometer data, and then even like being able to have highly sensitive detection of like gravimetric fields, so we can use this for like earthquake detection and prevention, thinking about surveying for like new development, new construction, and many other applications toward like sustainable cities. And so these kind of offer like a brief overarching highlight of where quantum sensing is starting to come into the market. Just to bring a little bit of nuance into why they are able to do that. And essentially, it comes down to the point of reference that you're using for measurement. And in this case, by interacting with subatomic particles, they are extremely sensitive to various factors, whether it's rotation, it's acceleration, it's frequency, it's electric fields, magnetic fields, gravitational fields. And so being able to actually leverage their sensitive nature and being able to actually, through electronic means, convert that into a signal that can actually, output some relevant information as it relates to sensing in these regards, that really sets quantum technology apart. If we think about some of the materials that essentially make up quantum technology, just to cover kind of like at a higher level, really have kind of 6 categories. You think about neutral atoms, where you are essentially thinking about how do I excite a atom into a higher energy level. And then there's an exact quantum frequency, a resonant frequency of that atom to get from ground state to the next excited energy level. And that frequency difference can now be tied to any other mechanism and any disturbance in the any controlled disturbance in the external stimuli or in the external environment can be detected. And then you can actually use that as a mechanism to recalibrate your system based on that resonant frequency of your neutral atoms. And so this is, very relevant when we think about, like, again, like magnetic fields, acceleration, maybe frequency as it relates to timing, which we'll go into a little bit more detail. And same with trapped ions. Again, that is, somewhat similar to this quantum state of neutral atoms, where we're really trying to tap into this frequency difference associated with energy levels of our ions in this case, as opposed to atoms. But it allows for different measured properties. And then photonics it's slightly different now. We're talking about entanglement, not of necessarily atoms per se, but of photons, essentially light. And so how do we create quantum sensing materials through the entanglement of light and any getting them into that entangled state, and then any disruption of that entangled state to then remove that would be a form of sensing. So it's essentially, how do we get them into this qubit description, whether it's an excited state or it's an entangled state, and any external stimulus that causes it to move away from that state will recalibrate to get these quantum systems back into the preferred state. And again, going through spin qubits, superconducting circuits, and even elementary particles, all of these revolve around that same concept concept of how do we create this quantum state, this kind of quantum qubit state, and maintain it as a form of sensing, because any external stimulus that we are looking to measure will get it out of that desired state, and we'll have to recalibrate to get these systems back where they need to be. A couple of or a few kind of quantum sensing like advantages, applications that get people very excited about thinking about how this applies. Again, there's a list of 8 here, and we can even go to detail or to discuss a few of these. I even think about spectroscopy, where these quantum sensors will provide much higher imaging capabilities because of the sensitivity levels that they afford of molecular structures. As we think about like proteins or nanomaterials, even compared to what's currently used in many research labs, which are electron microscopes. This offers magnitudes order higher sensitivity. So we can imagine the type of imaging we'll be able to perform using quantum sensors as opposed to what we've developed inherently in electron microscopes. Another example we can think of is even in the environmental monitoring space, where we look to monitor CO2 emissions through some localized measurement capability. Typically, the state of the art there can measure about 100 ppm CO2 emissions, and a lot of the research going on in quantum is improving that capability and reducing it down, by a magnitude of order to get into the 10 ppm range for CO2, allowing much more advanced detection and track and monitoring of our carbon CO2 emission reductions. And so that creates a lot of excitement, especially in the government realm, as they look to not only introduce new technologies, but start to think about how do we potentially maintain existing infrastructure, whether that be oil and gas. And we'll talk a little bit more detail when we think about timing here soon, about like navigation and even communication, and how that relates to like quantum sensing. But before we do that, I just wanted to really spend a little bit of time talking about where this market is and where we believe it will go. Again, a McKenzie report on quantum sensors. They did an initial analysis focused, on kind of, some of the most promising cases for quantum sensing, and projected that at a bare worst case conservative scenario, they anticipate this to be a $5 billion in annual revenue recurring market by 2030 at the latest, given the current market pricing for these technologies, which can range anywhere from like about $2,000 to upwards of, say $100,000, depending on the size and scale of that quantum sensor. But the thing that these reports, when I was diving into some of these analyst reports, they base it on, again, the fact that the current market pricing and the current growth trajectory based on these market pricings will stay the same. However, there's a lot of innovation going into how do we not only improve the performance, but how do we reduce the cost of these quantum sensors? And if that comes to maturity, we can see a major disruption in the MEMS market that it currently exists today, whether that's inertial sensors, pressure sensors, environmental sensors, optical sensors. There's a host of different MEMS technology out there, totaling about $80 billion now in recurring annual revenue, with a projected $200 billion market space. And so taking the portion of that quantum sensors can disrupt, given cost reductions, it really does create an exciting opportunity to look into and think about what are the challenges that are going to exist in order to get the cost down from this. And really make this a mass adoptive market that not only brings new opportunities, but it also disrupts existing markets. The QEDC, the kind of quantum consortium, they did an assessment on like quantum essentially sensing technology and their maturities and their impact as it relates to like national security interests, essential local US interests, mostly in the government space, but like a lot of that too as well in private applications. And as you can see here, they really identified the chip scale atomic clocks, essentially portable atomic clocks, as one of the highest potential impact areas as it relates to national security. above a lot of the other sensing technologies that are still coming to market. And it has demonstrated some early signs of success with continued need to improve performance. But nonetheless, I wanted to kind of to pivot and spend some time focusing a little bit on this kind of this space of atomic clocks, essentially quantum clocks at a miniaturized scale. But maybe just introducing atomic clocks in general, and then talking a little bit about the kind of the market at the chip scale level. And so atomic clocks essentially, again, are leveraged as sensors in a way that creates highly stable timing solutions. And so in this example here, we think about a GPS receiver. Maybe it's a phone, maybe it's a GPS receiver in a data center, and it's trying to synchronize its time across its network. Maybe it's for like data center network and messaging and communication, or it's for your phone and you're using GPS for navigation. As you can see here, as a signal from the GPS, from usually it's multiple GPSs, 2 to 3, maybe sometimes 4, is sent to a GPS receiver. That GPS receiver actually will take that time and recalibrate its time in case it's off. And so in order for that GPS receiver to view its stated time relevant to the time based on the signal received from the GPS, you need an extremely precise timing solution in the GPS satellites. And so atomic clocks have already been introduced into GPS satellites at a much larger scale. So we're talking about like maybe like a tabletop sized clock, much larger clocks. And they create extremely precise technologies because of their sensing capabilities and their ability to recalibrate timing solutions. And so you can see here in this kind of time and flight example, leveraging like quantum atomic clocks, you can demonstrate stability over 4 days without any drift in timing relevant to maybe a sensor, a conventional sensor that would demonstrate that same stability within a 1-hour period. And a brief example of this is if we didn't have extremely precise sensors that correlate to timing in our GPS satellites, and we incurred a 1 microsecond drift in timing, creating an error, that would result in a 300-meter error in GPS position. So as we can see, like it's extremely important to get the to leverage these sensors for precise timing, calibration, and synchronization across many different applications. I kind of created this categorized this kind of quadrant structure to think about like why people need timing and when it might be relevant for what type of timing, which we'll get into conversations about. Will lead into conversations about chip scale atomic clocks. Essentially, you can think about it from a group of devices like a distributed network. Maybe it's an IoT, maybe it's a data network, data center infrastructure, financial trading centers. There's a group of devices that need to be synchronized, or it may just be a single device. And then again, on the other axis, you think about, does it need just relative time, or it needs an absolute accurate time that's tied to these extremely precise GPS satellite networks? And so again, in quadrant A, where we think about single devices, relative time, that's usually lower threat. You think about like a stopwatch, a heart monitor. It just needs to, relative to itself, reset and provide some form of like accurate timing. It doesn't need to be tied into like a messaging system to communicate between two parties. And likewise with quadrant B, single devices. On this side, though, these single devices would require like absolute time detection. And so we think about, alarm clocks, watches, any a system that is relied upon for individual like time relative to other people assessing that same time criteria, and you want absolute time in that device, then you may want to look into thinking about a timing solution that syncs to like an absolute time metric. It syncs to UTC, which is the actual universal time system that's leveraged from GPS satellites. And then again, you start thinking about distributed networks, quadrant C, quadrant D, really quadrant C. It's more relative. So you're thinking, maybe smart grid. I just need to know, like, if I'm time stamping, energy transmissions, and you're trying to collect data around how the distribution of electricity is happening as relates to time, then you just needed to have it in relation to each other and not relation to some fundamental time that tracks over a period of days, just more so relative to each other. But then on finance, one that's very clear is, the in quadrant D, you think about financial trading networks, financial trading systems where, nanoseconds matter when it comes to the order in which like a stock was traded and confirming that price. And so financial trading centers care very much about having all of their distributed systems highly synchronized to some absolute measure of time, which in our case is kind of GPS satellites through the atomic clocks that are housed inside those GPS, that network of satellites. There's 4 different forms of like systems that have been timing systems that have been built to provide this sort of like quadrant style, like relative, versus absolute timing need. You have local timers, again, like we talked about, whether it's like, watches, even like phones, any like, portable devices, typically works around, they have some integrated local timer in there. And this often can provide, a timing solution with at lower power consumption, and it can provide timing solution in case like maybe GPS is inaccessible. And so, often like if you're, inside of a building or you're in certain environments where GPS signals are weak, then this can kind of hold you over until you resync with the GPS network. And then LTE signals, again, is another form of relative kind of timing. Again, cell phones also will ping, not only may they have a local timer, but they'll ping these cell towers to adjust to resynchronize their timing. And as they go in between cell towers, you can observe some signal like disturbance. And so it is not a perfect absolute time, and you will get some drift in the performance of that. And so as you can see, like these cell towers often have to resync to an absolute time, being the GPS, but they do provide an alternative timing solution to cell phones, for example. And then again, like network timing, we think about absolute time everywhere, messaging apps, even like streaming, FaceTime, like being able to have accurate timing when it comes to like relaying information between multiple entities. That's where like a network timing, maybe you integrate a timing system inside of the data center to sync with GPS and provide that extremely precise timing mechanism. And then finally, obviously, like I've been kind of harping on this kind of GPS, GNSS, absolute relative time that everything relies on. So everything gets resynchronized to this kind of GPS satellite timing mechanism. However, as we will continue this conversation, you'll realize that this kind of reliance on GPS and GNS as the absolute relative time is becoming more vulnerable and many people perceive as no longer sufficient. And so a lot of people are looking into these, ensuring we have enough hybrid timing solutions integrated into our electronics and our technology, such that the limitations of GPS and the concerns of GPS are mitigated. And that could be through increased resiliency, maybe providing an accurate timing output beyond what GPS can even provide in certain areas. That could be an increased reliability. Maybe it's improving the accuracy when GPS access is limited, signal strength is weak because it is a wireless transmission, or just increased availability where you're providing this kind of absolute time when GPS signals are obstructed. And so maybe you have a atomic clock that is as accurate as GPS at a local level such that it can replace GPS. And so these kind of hybrid timing solutions have become more of interest. And even REMA did a seminar back in April for this same consortium, talking about like, quantum technology as relates to like DOE. And I'm kind of like paraphrasing that the emphasis of that she stressed, but essentially there's this growing lack of trust that GPS, due to security reasons, is going to maintain itself as the dominant form of timing solutions, and we need to start thinking about other ways to assure timing remains robust. And quantum sensing is very much the area that they're interested in looking into. And again, that's because GPS fundamentally covers so many infrastructures and industries in our ecosystem that a single day of GPS failure would be highly catastrophic for our economy. Again, that's because of several reasons, man-made and just, natural, whether that's spoofing, maybe other countries, and interference, whether it's unintentional or intentional. Think about just general like signal errors and just data inherent in like electronic structures that we build, cyber attacks, and then just even like solar flares or things that can disturb the wireless transmission of like GPS signals. And so they're very much interested in thinking about this again, because looking at some economic scenarios, a researcher published that again, if GPS was to go down, it would could result in about $60 billion a day in lost economic activity because of our reliance on GPS as a timing mechanism. And so this increased nature of spoofing, jamming, and just general concerns has gotten people very much interested in how do we create hybrid timing solutions. And so again, atomic clocks, essentially these local chip, going back to like the chip scale atomic clocks that have seen such a high priority, it's because integrating this local miniaturized atomic clock into electronic devices creates a more assured hybrid timing solution, such that we can reduce our reliance on GPS and maintain our existing like technology infrastructure that's relying on timing, especially as it relates to position, navigation, and again, timing, PNT. And so a couple years ago, New York Article Times was published, just really highlighting the vulnerabilities about GPS, many of them which I've mentioned. And even on the congressional side, they published a National Timing Resilience and Security Act, which is essentially mandating, at least on the government side, the DoD and some other government agencies, to start to institute these hybrid timing solutions to reduce their reliance on GPS across, any infrastructure that's government owned. And eventually, hopefully, in the private sector as well, where there's banks, hospitals, the power grid, they really want to see this kind of newly thought about hybrid timing system come up. And so that kind of like hopefully explains a little bit about like timing and then landscape. I wanted to now explain further into like why the chip scale atomic clocks are, how they work and why they're relevant, and again talk a little bit about mesoquantum. But again, chip scale atomic clocks, these local timing solutions, will serve as the holy grail for highly precise local time sources. Because essentially the way they work is, if any electronic device has a local oscillator, like a crystal oscillator that they use, say that fluctuates at 32,000 times a second, you can use that 32K as second reference. But these crystal oscillators drift. Their stability and to maintain that frequency is poor, and so you're not able to get accurate timing just off of these local oscillators. And so in some cases, people will rely on GPS again to resync the oscillator as it starts to drift off. But again, as we think about this new hybrid timing solution ecosystem, integrating what we see here as the physics package, which is the atomic clock reference locally to recalibrate, creates a much more exciting opportunity for this kind of like timing, new timing solution ecosystem. And so again, that raw signal from the oscillator will go into some frequency conversion. Often, you know, it has to convert it to like the gigahertz for it to be read by the physics package. But then again, that, as we talked about, the exciting the atom in the physics package at its resonant frequency, it'll read relative to the signal that's inputted into it from the local oscillator. And if they're not in sync, there will be an error signal detected, and then you can have a control loop and some tuning to retune the oscillator and then put out this accurate timing clock output. And so this is a very much a local mechanism that's going to occur instead of this wireless GPS to electronic device system. And so that's what we are bringing Mesoquantum as our first kind of quantum sensing technology, is this ability to leverage a kind of quantum principle to, you know, locally adjust a timing system inside an electronic device. Again, this is based on the increased need for resilient, reliable, and available timing. And so this kind of unlocks this growing market of local timing using ultra precise timing mechanisms, again, as a GPS substitute. When we think about, you know, offshore oil and gas exploration, where GPS is limited, especially in the underwater sensing environment, we think about military and their need for, you know, maybe some downrange operations that have limited GPS capabilities, or just as a reliable backup in case for any reason GPS signals are down, there's issues, and now these data centers, these communication centers can maintain function and operation and have accurate alignment over a long period of time relative to the crystal oscillators that will drift and then timing, create inaccurate timing. And then obviously in the GPS complementary side, where there's certain areas that GPS still just, you know, due to like wireless transmission and timing of synchronization, may not have the ability to create as an enhanced of a timing accuracy signal as a local device. And so integrating these kind of local timing systems in self-driving cars will improve its ability to navigate roads, even vertical resolution inside of buildings, understanding what floors you could be on now, because GPS struggles to have vertical resolution, but having these, you know, internally highly accurate timing systems can now think about vertical resolution, even, you know, in autonomous warehouses. You think about autonomous warehouse robotics, and again, some of the limitations of GPS when it comes to like internal systems. And so these are some of the exciting areas that this kind of like local timing solution can be applied. And again, just to kind of capture, we fundamentally believe that the future of the atomic clocks is going to be an everyday technology. So that's what we're excited about. You know, I kind of listed some of that: self-driving cars, low Earth orbit satellites, GPS, data centers. I can't harp on this enough. And as a team, the researchers and at CU Boulder NIST have demonstrated a technique to improve the performance, i.e. stability of the atomic clocks, about a magnitude order for these chip scale miniaturized atomic clocks, about a magnitude order than what's existing in the market. And again, stability is a critical performance metric. One, because the length of time before you would need to resync a atomic, before you would need to resync to the absolute time measurement, which is GPS, can be extended. And so for many operations, like you think about underwater sensing, where they may sync on the shore, and then as they go underneath ground or underneath the water, they can no longer have access to GPS. It's important to have a longer duration of stability when you're not tied to that. And so those type of applications are extremely important to have increased stability, amongst others. And we've been able to approve that. And now it also just even gets us into the realm when we talk about this new hybrid timing solution. At 10 to the minus 12, we start to think about, you know, actually having the performance where people can input this as just a GPS reliable like backup period, whereas some of these other miniaturized chip scale atomic clocks, they do not perform at the level that can be integrated into certain local electronic portable devices. And so this creates a new market opening once you hit this kind of stability performance level, such that we can be perceived, somewhat enhanced as a resilient mechanism for GPS. And so right now we're working on commercializing the technology. We've demonstrated at the lab scale that we can improve the performance. We're looking to build out this prototype, again, at the low size, weight, and power metric. Again, ideal for remote and portable applications. And then that's the goal that we're moving forward to. And ultimately, our chip scale atomic clocks will be the lowest size, weight, and power atomic clocks, especially at this improved performance. And so this graph just shows a linear trend between the stability and the performance of a clock and the size, weight, and power of that power requirement of those clocks. And so you can see, you can get higher stability, such as the clocks that are in the GPS, but they're much larger, much heavier. And so as we think about portable, electronic, miniaturized devices, we've been able to improve the performance of that. And we're excited to kind of bring this to market. And so again, I know I'm pushing up on time here and I've kind of run out, but again, like these are some of the markets that we've been exploring and we've been able to get some exciting customer feedback in, is again, the smart grid time synchronization, each of the power nodes, and being able to like help distribute like accurate like timestamps as it relates to like electricity distribution, and then even underwater sensing where your microwave, your RF links from are no longer available underground, and so you're using other forms of like acoustic and optical like sound booms to generate information, and you're going to require some form of like highly precise timing mechanism to trust that as these underwater sensors communicate with each other, they're not relying on GPS for synchronization, but they're still highly synchronized. So far, again, we've licensed the IP out of the university. We've been awarded some fundamental grants to start to purchase equipment. We solidified some LOIs as far as like getting up to about 100 CSACs for initial production, confirmed if once we produce those, and then currently have a pre-seed offer in hand. We just received about a week ago from a VC, and so we're very much looking to move along with this based on our milestones, which by the end of the year we'll have demonstrated our physics package outside of the lab in our own facilities, file the subsequent IP necessary. Look to raise our next round based on that, and then have our fully integrated chip scale prototype outside of the lab developed that's miniaturized, and then start to demonstrate user testing and performance improvements at that point, and then from there on, you can see it's mostly focused on sales and scaling and production. And so that is hopefully a general overview about sensors, atomic clocks, what we're trying to do. The founding team on MESA consists of a PhD student getting ready to graduate here out of the NIST CU Boulder. Quantum Partnership, a postdoc who has several years building these atomic clocks out of CU Boulder, NIST, and then myself, who has experience with R&D commercialization out of the research labs, whether that be academic or government, and developing business acumen and venture capital experience too as well in the process. So very much excited to be a part of this journey, and very much excited to bring a pipeline of innovation, because it just doesn't stop with atomic clocks. The fundamental ability to leverage these physics packages, these sensors for all forms of sensing capabilities is what we are working to bring to market, starting with atomic clocks. And if you are interested in all and want to get in contact with us, I'm happy to leave my personal email in the chat as well, but this is our general email that the team will see and would love to stay in touch. So that is my presentation there, and I can stop there if you would like to pause and be open to any questions.
Yeah, no, that's an awesome presentation, Wale. Thank you. Really appreciate it. I do have a few questions, and then we'll open it up for the audience to ask you questions. So I have actually more than a few questions, but I'll start with one.
No problem.
Yeah. Your first, I saw in your slides, you said that the market for quantum sensors is right now. And the market size right now is about 5 billion, or by 2030, it's going to be 5 billion. What is stopping the adoption of quantum sensors right now?
It's honestly a cost. It's the cost, because when you think about crystal oscillators, you can honestly get them on the market. Like Apple has them integrated in there as a spare.
Yep.
Looking at this hybrid timing, for about maybe less than $5. And when you think about that, you realize that they would much rather have their kind of users deal with like delayed inaccuracy and like navigation and things like that because of the cost. And so $5 versus 5,000 is just something that, I mean, you would never be able to sell a phone off of that. And so needing to not necessarily get down to the $5 level, but having breakthroughs to get down to the sub 500 level will really start to see like a much broader adoption in the technology. And we're very excited about this space because, you know, we've realized that many of the labs have continued to innovate in this space, but I think a lot of the providers of like timing solutions have kind of just leveraged it to, you know, add more as a revenue generating product or technology. And many of them don't have an fundamental like R&D labs still instituted in their companies. And so there's a mismatch in the market between like how do we continue to innovate, which the labs are doing to reduce costs, versus what the companies are actually commercializing. So there's like an interesting opportunity there.
One follow-up question, and this is again going to the GPS side of things. So you gave an excellent slide on where GPS can help and stuff like that.
Yeah.
If I am using GPS today and it's precise, right? I understand that if something happens, I have a bad day. I'm not a bad day. It's just like, it's really going to be bad because if we lost the sync, right? But what is the motivation for me to buy a quantum sensor? And I can say security may be one, but the amount of money that I need to invest. What will motivate a user to buy a GPS atomic clock? Oh, sorry, quantum atomic clock, I mean.
Yeah, no, that's a great question. I think, you know, I'll go back to like a couple of slides here again, and just maybe like, you know, stick around here a little bit more. There is essentially like there's like existing market that already has timing solutions, and they are fully like satisfied with that as it remains right now.
Yeah.
However, again, I stress that market is excited to continue to improve the performance of the technology. I mean, they're going to continue to innovate, improve the performance of their electronics, you know, components, as long as the prices are reasonable for their products. And so it's not as if it's not already in there. Like the time solution the local timing solution doesn't already exist. It's more of a matter of can you get the cost down such that they're going to choose the most precise timing solution, like, you know, relative to the cost. But there's also this new market again, and where we really think you'll see a lot more adoption of quantum sensing initially before you integrate into the older market. And that's you know, places where like offshore wind construction projects, where they essentially, you know, what they do is they'll calibrate all of their sensors using GPS, send them underwater, get the information to understand where they can do their construction project. However, they have a limited amount of time because it's going to eventually drift. And then now the accuracy of your signal from the ground, from the seafloor up, becomes inaccurate. And so if they can prolong that without having to bring their sensors up water, it saves on maintenance time. It saves on cost dramatically because they can prolong their operations and they don't have to replace those components as frequent. And so there creates this like incentive to like improve the performance of timing from that spectrum. And then again, like when we think about a lot of these autonomous vehicles, the performance level of so I say like the local timing devices is not sufficient enough to where they can rely on it to actually drive the its ability to navigate its environment. And so like an example of that is if you have multiple autonomous vehicles, driving, everywhere, they're sensing the environment. If they have these extremely precise atomic clocks, you no longer need to send a signal and bounce it there and back. It can literally just go one-way signal because you know that the other vehicle, the other system has the same precise timing. And so now you actually can increase the accuracy of that signal because you're only doing one way versus like relying on like there and back bouncing free signals to detect your location and your environment. And so that's one way where by having extremely precise, you can enable this kind of autonomous world, this autonomous space to kind of grow and expand, especially autonomous warehouse robotics, things like that. You can really allow that to start to flourish in a much more advanced way.
Perfect. Thank you for answering my questions. I see a few questions on the chat. I think the first one is from Andrea. And yet, you want to unmute yourself and ask the question, or do you want me to read through it?
Okay, yeah. Yeah, I see the question. What type of supply chains are needed for? It depends on the type of quantum sensor. Typically we'll use like a vapor cell laser, like a VCSEL laser, to excite the atoms, whether it's like rubidium atoms. I didn't go into detail too much about the technology, but essentially if we're using like a droplet of a very small amount of say rubidium atoms, we'll use a VCSEL laser to excite those atoms, and then you'll typically have some form of like heating element to ease the ability to get those atoms into its excited state. And so there's certain temperature requirements. And so we'll focus on hermetic sealings and other forms like heating systems to actually generate the temperatures we need. We'll also think about, again, like you need to insulate it actually from its surrounding environment so you can control the sensing. And so, you'll typically have like, Faraday, type cage structures to isolate any form of like field interference, magnetic interference, electric interference, things like that, and only focus on the type of sensing we want. And so in general, when you think about like the coherent particle trap system, the CPT systems, it's structured around there. Other kind of quantum sensors are built, differently, but like in our regard, those are kind of the primary components. And there's a lot of electronic systems surrounding that, phase modulators, things like that, to like really get the output that we want to read out properly. But those are kind of like some of the key technologies, being the laser we use to like excite the atoms and like how we actually like contain the environment. So anyways, hopefully that kind of gives you just like a general high level of what's going on there inside the physics package.
Thank you.
Quantum entangled communication. Yes, that's quantum entangled communication would really bring local timing devices to the GPS level. And so very much an exciting area of research where there's labs at Caltech focused on this, labs at MIT also focused on this, really trying to leverage not just exciting like individual atoms to like ground, from like ground state to their higher energy state, but actually getting quantum entanglement and using that as a sensing mechanism, because of the enhanced sensitivity you get from the entangled state as it relates to, relative to even what we would do with like single atoms. And so there is some work being done with that as well, and not just on the kind of like traditional qubit side, but even like on the photonic side, and thinking about entanglement with between photons. And so.
So further to that, Prakash here again, since you mentioned that sensing and communications are far ahead of computation, and sensing being the low-hanging fruit, when
Yes.
you say entangled communication, the one you mentioned previously were like V2V or something like uh, those kinds of application for the precision atomic clock. But is there anything that we can apply in this quantum entangled communication, which will be of those ABCD types you mentioned, which will be relevant here?
Sorry, just to better understand that
So
question.
is there an application of the specific types of clocks for entangled uh, communication, quantum entangled communication?
Yeah, so yeah, that's a good question. I don't have too much knowledge in that regard. I know that some folks are doing research to actually like leverage this in building out components for quantum computers, actually, because being able to actually sense like the quantum entangled state is a whole nother area of research as well. And so having enough sensitivity and leveraging like these extremely precise sensors, maybe not tied into like a crystal oscillator or anything like that, but just like these kind of quantum sensors, integrated into like these kind of quantum computing architectures can help with like sensing mechanisms of achieving qubit, like how many qubits you have, the length stability of your qubits, things like that. I'm not sure that it directly answers your question, but when I know it relates to quantum computing, at least like this area of like quantum sensors, even like atomic clocks could be, and people are looking to apply that there as well into like unlocking quantum computing sensing and measurements in those regards.
So predictions regarding earthquakes, predictions regarding the events, can that be applied there?
Oh, okay. Thank you. Yeah. Okay. Sorry. Yeah. That's helpful to get. Yes. Yeah. So the fundamental benefit of these kind of quantum sensors in the quantum clock is the physics package that you build around it. And so in this case, we're relying on a particular alkaline alkaline metal, rubidium, and exciting that to generate our sensing mechanism. And so you can build the electronic components around it to essentially convert whatever signal you get, whether that's a gravitational field, like gravitational signal, magnetic field, signal from magnetic field, anything like that. You can convert it into a signal that can be detected by that physics package. And the signal that you seek or desire, if it's not in sync with the resonant frequency of the physics package, you can create a calibrating loop to maintain ultra precision, whether it's for earthquake detection and like gravimeters and sensing that, or again a host of other like inertial acceleration, things like that. So the fundamental principle is you build the electronic systems out to get a signal input, convert it into a signal that the physics package can read, and then you recalibrate at the local level. And so yes, and that's one of the reasons we are very much interested in this space, because we can take our physics package, apply it to gyroscopes, apply it to accelerometers, apply it to gravimeters, apply it to a host of other sensing needs depending on the application.
Super. Thank you.
Yep.
Thank you, Wale. I know I see we are at time. And I think there's one last question. Let's see, we'll take that last question and then we'll be done for the thing. Do you want me to read it, or you can read it yourself?
See, does the precision standards for chip level, I'm assuming are there precision standards for chip level atomic clocks. Yeah, please feel free to chime in and jump in if I'm not answering this correctly, but there's no I would say there's no standards for their performance levels. It can definitely range. The protocol like precision standards, like whether it be like NTP or what Facebook has kind of Meta's put out with PTP, those are more like precision timing standards that people are building their timing solutions around. And so if the chip scale atomic clocks can meet those timing standards, one thing I didn't really mention in this, but happening in more detail later, is that power consumption is also becoming a big thing too in electronic systems and devices. Like with AI and all this new computing, any device inside of a electronic system that's consuming more power than desired just increases cost, and it makes it difficult to run these kind of data centers. And so as they look to improve their kind of like precise timing like protocols and standards, they're also thinking about how do we reduce power consumption of our electronic components. And so yeah, getting that down would help also integrate these kind of chip level atomic clocks into like a variety of different systems, not just like cost, but like power as well. But anyways, yeah, so they don't have a particular standard right now in the market. They're around 10 to the negative 10 stability wise, which you can convert into like a certain like stability over a certain period of time and take it to negative 11. But yeah, hopefully that maybe touches on the question somewhat.
No, I have a follow-up on that. I know I said last question, but how many chip level atomic clocks are even there right now? I mean,
yeah, no, thank you. That's a good question. So the European Union actually put out a report. I want to say in 2020, was it, that they put a report about chip scale atomic clocks and like the journey and the history of it, and they engaged with some of the customers, and you can see some of the kind of market reports. But you're essentially putting out about 50 to 100,000 of those a year. These kind of like chip scale atomic clocks at price points that range between like 5K to 10K.
okay.
And so you can kind of do the math to see like what's happening now, and it's very much in like defense applications for like secure environments.
Yep.
Some like underwater sensing applications, but a lot of these new emerging technology markets, it's yet to kind of penetrate. But again, like many people are deterred by that 5K timestamp. But like even like in like geosatellites and stuff like that, they're also being put into those as well, because those are much smaller form factors. So you can't use these gigantic clocks that you do in the GPS satellites. You need something with a much lower power consumption and lower size form factors. So those are some of the markets that they're being used in, and that's just going to continue to expand as the technology innovates, and other exciting technology comes to the market as well. So
cool. Thank you,
Great.
Wale.
Yeah.
Really
again.
appreciate you coming here, and thank you everyone for being part of this conversation. And you can contact Mesa Quantum, or you can contact Wale directly. He will put his email address if you're okay with that.
Right. No.
Yeah.
Yep.
Thank you. And with that, we'll end our meetup for today, and really appreciate it, Wale.
Oh, absolutely. Glad to
Thanks,
have
thanks,
you.
Wale and Taposh. Great show.
Yeah. Thank you. You guys have a good day.
Good night.
You too.
Bye.